Hello everybody, I'm Andrea Campanella from the Open Networking Foundation, and today I want to bring you a demo of VOLTHA, the virtual OLT hardware abstraction, which is a production deployed disaggregated open source solution for broadband networks. In particular, I'd like to thank Girish, Hardik, and Matteo that with myself or the team at ONF that worked really hard on this project and on the demo that you're about to see. So why is ONF going into the disaggregated or OLT space and have decided some years ago to pursue this project? Here on your left, you see a traditional chassis-based vendor OLT for passive optical networks. It's a vertically integrated element that comprises an element management system with the capability to manage different VLANs and protocols such as AGMP, PPPoE, multicast, authentication. This chassis comprised both PON MAC blades for the passive optical networks, but also compute blades for packet handling and elements like that. Usually this was a vertically integrated from the same company providing hardware, software, and not just the OLT hardware, but also the ONT, ONU hardware, that is the equipment that goes into the subscriber's home. So once you wanted to change something in this whole equipment, in this whole solution, you would most likely have to buy, again, the whole thing. And it was not flexible enough for today's very fast-paced, accelerated environment, especially with the surging demand in broadband networks. So we at ONF decided to apply some SDN principles to this vertically integrated element and virtually integrated passive optical networks, and they came up with a solution that starts on the bottom with a white box OLT with the spec that is published under the Open Compute project. And this is the hardware, just plain hardware, on top of which we deploy in Kubernetes running on servers on the premises of the service provider, VOLTHA, which is comprised of several microservices, and we'll talk about that later, and it controls both the OLT and the ONUs via an OMCI stack. On top of this, we deploy the SDN controller with several applications that control VLAN tagging, AAA, multicast, PoE, etc., and the two communicate via OpenFlow. The code of VOLTHA is completely open source under the ONF GitHub pages, and the design of the white box OLT is under the Open Compute project, and there are several vendors of OLTs that have now become white box OLTs where we can deploy the Open OLT agent. So let's dive in a little bit more into VOLTHA itself. But before we do that, let me remind everybody that right now, VOLTHA is in production. So the solution I'm about to show you is in production since 2020 in Deutsche Telekom and Turk Telekom with live customers. So first of all, as we said, we start with some ONUs. And then you have the white box OLT. Within the white box OLT, we deploy two elements. An Open OLT agent, which sits on the box and leverages the BAL Broadcom SDK to control the chipsets, and the device management agent. Let's start first with the OpenOLT agent. That OpenOLT agent, via a gRPC connection, communicates with an OpenOLT adapter. This in conjunction with the OpenONU adapter forms the layer of southbound adaptation towards the hardware. So they control the OLT, but also via an OpenOMCI stack and library, all written in Go, as these two adapters are, the ONUs themselves and propagate the EMIs necessary for the configuration of those ONUs. On top of those, there sits what we call a VOLTHA core, which is responsible for handling all the requests from the northbound and the events from the southbound, and appropriately making decisions on top of these. And on top of that, we have the OpenFlow agent, which is what exposes VOLTHA as a single switch to any SDN controller on the northbound. The VOLTHA core, the adapters leverage etcd as a storage backend for their information in order for them to allow a restart of those themselves, of the adapters, without any service impact, as you will see in the demo. So on top of the OF agent, we deploy usually with VOLTHA the ONOS SDN controller, which manages the VOLTHA OLT and ONU as a single switch with NNI ports of the OLT on one side and RG ports of the ONU on the other side, so UNI ports and NNI ports. On top of ONOS, then we put some VOLTHA specific applications. ONOS is a modular platform where you can load applications, and in particular, we have some applications that, along with all of the rest of the stack, publish events on Kafka, the Kafka bus, for consumption, and you will see again this later in the demo. So this set of applications, they are comprised of the OLT application that does flow handling, mainly like VLAN tagging, etc. The AAA application for authentication, such as EPOL. Then we have the HTTP L2 relay for the HTTP packets. And we have SADIS for the subscriber information, such as the VLAN tags and the bandwidth profiles. Then we have IGMP proxy, Kafka, PPPoE, but also another example that can be added or not, depending on the workflow, is multicast. All of this is also put together with another interface, which we call the device management interface, which does non-data path related operations, such as inventory or update of the OLT software, or measurements of elements that are not related to VOLTHA, like the fan speed, for example. And this goes directly to whatever management system the operator has on the northbound of VOLTHA. So with this, here you're going to see the demo setup, and I'm going to leave it to Matteo to explain it live and showcase some of the features that VOLTHA has in the production deployments that we have, and the capabilities that we offer to operators and service providers that choose VOLTHA.
Welcome to the VOLTHA demo. We are here to demonstrate how we can use our software to control a traditional passive optical network. So what we have in this setup is described in this slide. So our software is deployed on top of a Kubernetes cluster that runs in this equipment. And if we look at this demo setup, we can imagine that this section of the hardware is actually running in a service provider data center, so out at the edge. We have a single node Kubernetes cluster. In production, it will be deployed as a 3-node cluster for resiliency. For the demo, 1 node is more than enough. All of our software, as I said, is deployed on this cluster, and it controls both an OLT and a switch. In this particular case, we're using a Radisys 1600X OLT that is an any-PON OLT, and thus can be configured to support both XGS PON network and GPON network. In this demo, we are displaying functionalities on a GPON network. Now, our OLT is connected to the switch, and the switch on that side is connected to our BNG in the central office. From the OLT, we have 2 PONs, optical networks, that are going to the subscriber premises. So everything you see on top of here, you can imagine being in a subscriber house or in his basement. And we have 3 different ONUs. As you can see, these are different models. 2 of them are connected to emulated clients, and 1 of them is connected to our demo laptop. As you can see, at this point, this laptop cannot go out to the internet, but that is expected as nothing is configured yet in the cluster. If we take a look inside the Kubernetes cluster, there are 2 important pieces to look at. The first one is what we call the VOLTHA infrastructure. It's a set of components that are used either in support of VOLTHA or to configure the networking aspects of the optical network. So we can see we have etcd, that is a highly available, highly scalable key value data store that is used to persist the data that VOLTHA needs to operate. We have Kafka, that is a message bus that is used to expose events to the outside world. We'll see an example of that later on in the demo. And we have ONOS, that is an SDN controller created by ONF. And it's used to program the flows in the network. The second important piece to look at is VOLTHA itself, and it is comprised of 4 components. We have OF agent, that is a translation layer between OpenFlow and the VOLTHA internal APIs. We have the core that provides the abstractions between the logical device and the underlying physical optical network. And we have a set of adapters. The adapters come in pair, and the 2 that you see here, the OpenONU and OpenOLT adapters, are based on open specification that many vendor has adopted, so that they can be used out of the box to control a certain set of devices, but there is nothing that prevents you to create an adapter that works with your own device and its internal API to work with VOLTHA. If we go inside ONOS and we take a look at the system, we see that we have one device that is configured in the system. This is the aggregation switch that we showed before, and it's used to connect the OLT, in this case only one OLT, to the BNG. As we can see, we have 2 ports enabled, port 1 on which the OLT is connected, and port 31 to which the BNG is connected. And we also have configured a set of rules to connect the traffic between these 2 ports on the specific customer VLAN for this setup. If we now take a look inside VOLTHA, we can see that no devices are configured yet. So we can just go ahead and enable our OLT so that it will come out and immediately enable the ONUs that are present in our setup. As you can see, they are going through some initial configuration and being activated. They're now available, and the OMCI exchange between the OLT, the OpenONU adapter, and the ONU devices has completed. So we can go in ONOS and see what is the view that the SDN controller has of the system. We now have 2 devices in ONOS. One is still the aggregation switch that we saw before, and the second one is the OLT that is represented to the SDN controller in the same exact way as the aggregation switch does. So if we check the ports on the OLT device, now we see it is represented as a switch with 4 ports. The last one is the NNI port, so the port that goes from the OLT to the switch to bring the upstream traffic to the network. And we have 3 other ports that are the UNI's port present on the ONU. And ONOS doesn't know anything at this point about those ports. So I can just go ahead and provision a subscriber on one of the ONUs in the system. In this case, we're going to provision port 256 because that's where our demo setup is connected to. once I do that, Onus will create the flows to allow our subscribers to send traffic out to the internet. But be aware that in the real world, this won't happen via the Onus CLI. It will happen through some external system that will listen on the Kafka events and react to those and provision the flows. We can now check the flows that have been added for our OLT device. And we can see that we have 4 specific flows for our subscriber. 2 represent the upstream traffic, the one that are marked with import 256, and 2 are for the downstream traffic. So at this point, if we go to our demo laptop and we try to reload the page, our subscriber will be able to navigate out to the internet. During the previous step of the demo, we discussed about the events. We can see how we can listen to events that are happening in the system. And these are all the events that had happened so far regarding the device. We're now going to reboot one ONU to give you an idea of what are the events that an external system can listen to react to changes in the PON network. So we see that our devices now went on and generated few PON-specific events, and in particular, the one that an operator might be interested in to manage the flows is the device state change event. Now we are bringing the device back up, and we'll see that as soon as it connects back to the OLT, we'll get a new set of events that the operator can use to trigger the flow provisioning for that particular subscriber according to its own logic. As you see, the device now rebooted, and we went through some events. We cleared the dying gasp, and the ONU went through the state changes in its state machine to be brought up back and configured accordingly to what we had in the system. And the last event we had was the ONU activated, and this would be the trigger for a state machine to provision the flows in the subscriber workflow. Now that we have provisioned our subscriber and our demo laptop has acquired an IP and is able to go out to the internet, we can take a look at some other details of the configuration. We saw before that we had configured the flows for the subscriber with CNS tag 2222, and this information are coming from one of the applications that runs on top of Onus that is called SADIS. In this particular demo, all the information are configured locally, but again, this is just a demo, and SADIS is perfectly capable of going out and fetching this information from an external service, and that's what will happen in a production setup. But we see that our subscriber was configured with an S tag of 2222 and a C tag on 4096. That is a placeholder tag that we use for any tag, because what we are displaying is Deutsche Telekom, and for them, the C tag is completely transparent to the VOLTHA system. There are some other informations that are contained in the subscriber configuration. For example, the technology profile ID. Now, the technology profile is something that is very PON specific and is basically a configuration of the schedulers and the queues that needs to be programmed on the OLT for a particular subscriber. And VOLTHA can accommodate to have multiple technologies profile if needed for different subscriber, but in this demo, we have the same for all of them. Another important thing that we're going to demonstrate now is the definition of the upstream and downstream bandwidth profile. As you can see, we reference them with a string identifier. And again, the profiles for the demo are loaded inside ONOS, but can be stored somewhere else in an external system, and ONOS is capable of going and fetch them. We saw that our subscriber has a downstream bandwidth profile with an ID bandwidth 2. This bandwidth profile has a guaranteed information rate of 100 megabits per second, has a committed information rate of 100 megabits per second, and has a best effort information rate of 300 megabits per second. So now I'm going to split my screen, and you can see on the left, I'm connected to our BNG. So I'm just going to start an Hyperv server on this machine. And on the right side, I'm connected to the client that we just provisioned. So when I run an Hyperv speed test between our subscriber laptop and the BNG, we see that given that there are no other subscribers provisioned on that PON, we get very, very close to the best effort bandwidth limit that we just configured in Celis. So far, we have demonstrated how it's easy with VOLTHA to configure a system from scratch and enable a subscriber to go out to the internet. But it's also important, once your setup is up and running, to make sure that everything is working fine. Now, the ONU we have been using for this demo was this Sercom A010-8 ADF. So we want to make sure that everything at the physical level is fine with that ONU. And that's why in VOLTHA, we implemented the ability of fetching PMs directly from the device. For example, we can go into the system and ask to have information about the status of the optical devices within the ONU. So we can see information like the optical power, the temperature, and other important information to make sure that the system is currently working as we expect it to be. In the same way that it's important to monitor physical information about the devices to make sure that the system is working, we need to be able to intercept events. So, for example, if we unplug the PON network from an ONU, the operator needs to be notified about these events. And we see that now events confirming what's happening in the system. And as soon as we plug the PON back in, we'll get this new set of events that are basically clearing the alarms and bringing the subscriber back online. When you're running a solution like VOLTHA in production, it's very important that the solution is resilient to failure. And this is something that we managed to build in our software thanks to the migration to the cloud best practices that are adopted in many cloud native projects such as VOLTHA. So as of now on my screen, you can see our client that is pinging out to the internet through the system. And you can see the VOLTHA components that are running onto the Kubernetes cluster. We're now going to emulate a failure, basically deleting an adapter. So I'm now going to stop the OpenOLT adapter, and we'll see that the adapter will go down, will come back up, will synchronize the device, and nothing will be affected in the data plane for the subscriber. As you can see, the OpenOLT adapter is now not running anymore, and it just restarted. A new instance came up, but nothing in the connectivity for the subscriber was affected by this operation. And this is nothing but something bad happened in the system. An error occurred. One of the nodes in the Kubernetes cluster went down, and everything happened at the software level. We were able to reconcile the device so that the traffic is not affected.
Thanks, Matteo, for the great demo. That was indeed very insightful, and it really provides an overview of all the capabilities that VOLTHA has. So let me remind some of those as a summary of this demo. So VOLTHA has the capability to completely hide the pawn level details from higher levels. As you have seen in Onos, we only see the UNI ports on one side and the NNI ports. So the whole pawn is viewed as a switch, as an Ethernet switch, effectively. VOLTHA supports XGS PON, GPON, and EPON technologies. We have different brands of OLTs and ONUs with multi-UNI support on the ONUs. We can support multiple services. In the demo that Matteo has shown, we were doing HSIA, but for example, for Turk Telecom, we do voice over IP, video on demand, IPTV, etc. We support different workflows. The demo was done on the Deutsche Telekom workflows, but we have the AT&T workflow, the Deutsche Telekom, and the Turk Telecom workflows as well. And we have several other types of protocols that we support: EPOL, PPPoE, DHCP, Relay, etc. We do have the device management interface, as we discussed before. We have a full alarms and performance measurement suite, as you have seen. And very key, and we'll talk about it in a second, we have a scale support. We can support 10,240 ONUs in a single VOLTHA pod with one infrastructure and 10 stacks. One infrastructure is Onos, etcd, and Kafka, and 10 stacks are 10 replicas of the core, the adapters, and the OF agent. Each stack can support 2 OLTs up to 512 ONUs each. We have an extensive test suite with 180 plus nightly tests on hardware and software. As you have seen in the demo, we can do failure handling of the software with no data plane impact, and also the component software upgrade with no service impact, leveraging the same restart procedure that Matteo has shown. Also, we can support ONU software upgrade directly via our OMCI stack. So let me just dive a little bit deeper into the scale numbers that VOLTHA supports. As I've said, with 10 stacks enabled at one time, we have one stack comprised of the OF agent, the core, the adapters. 10 of these are supported with one infrastructure, which is a 3-node cluster of Onos, a 3-node cluster of etcd, and a 3-node cluster of Kafka. We can support up to 10,240 ONUs in a 3-node Kubernetes cluster. So that is our current requirement, and this can sit at the operator on-premises data center, where they deploy the Kubernetes cluster, and on top they deploy the infrastructure and the stacks. Each VOLTHA stack can go up to 10,240 ONUs in a combination of one or more OLTs. Usually we do 1,024 on 2 OLTs, 512 each. And for more information, you can actually go and see the VOLTHA scale measurements we do on Jenkins, because we test this scale nightly, actually more times a day, for all the workflows that we have. So AT&T, Turk Telecom, and Deutsche Telekom, we test that we keep up those scale numbers that we have set. So right now, let me finish up with a little bit of VOLTHA 2.9 roadmap, and also a little bit more forward-looking. So what we're doing, and we have actually completed this, we are migrating from Kafka to gRPC for the VOLTHA intercommunication service communication. In VOLTHA 2.8, we had Kafka in the middle between the adapters and the core. Right now, we moved away from that and just use Kafka for external events. We also have expanded our, we want to expand our scale numbers tenfold, so to 100,000 subscribers from the 10,000 we have right now in a VOLTHA pod. We want to expand our test suite upgrade to BAL 3.10, 3.12, in any case, a long-term support version. We also want to have MPLS support, a full complete IPv6 stack support, include voice, plain old telephone service, and also collaborate with the broadband forum, especially integrating into the cloud CO architecture. So in conclusion, ONF and the VOLTHA community have delivered through VOLTHA and ONOS a full open source, cloud native, disaggregated broadband solution that is feature rich, stable, scalable, and is deployed by tier 1 operators. If you're more interested in more information, you can go check out these two links, and I'll have the slides linked at the bottom of the video, so you can go check it out, which describe in detail the A4 deployment with the Deutsche Telekom and the SIBA central deployment with Turk Telekom. Also, you can go to docs.volta.org to learn more about the project and also try it for yourself, because we have a full virtualized environment that you can try on your laptop. Finally, let me just thank everybody in the SIBA and VOLTHA community that really has come together for achieving this amazing results that we just showcased today. So there are many, many companies and many players and many people that I know very well and have contributed greatly to this success and the production deployment of this project. So let me thank all of them. I cannot go one by one, but there was a great contribution from a lot of companies, as you can see here. So thanks a lot for listening to our demo and to our overview of VOLTHA. Please, if you have any information or question, just drop us an email. Mine is andrea@opennetworking.org. It's just first name @opennetworking.org for everybody in the team. Thanks a lot and have a great rest of your day.